Hello, this is Dmitry Bertsekas. I'd like to welcome you to this third of 5 lectures on semi-contractive dynamic programming models. These are models where some policies are well behaved and have contractive-like properties, while others are not. In the first lecture in this series, we looked at examples which illustrate the kind of unusual or pathological behavior that can occur in the semi-contractive problems. We also saw how we can avoid this kind of behavior through appropriate assumptions. In the second lecture, we gave a more detailed mathematical analysis for a special case, the important and popular class of stochastic optimal control problems, particularly stochastic shortest path problems. In this lecture, we are going to look at more general abstract dynamic programming models. We're going to extend the semi-contractive model, and we are going to also extend the results that we gave for stochastic optimal control problems. In the fifth and sixth lecture, we are going to discuss various applications to the broad classes of problems and also computational algorithms. Let me give an outline of this lecture. We're going to first introduce a mathematical model of abstract dynamic programming, which will serve as a unifying vehicle for broad classes of dynamic programming problems. We're going to illustrate it with various special cases, including stochastic optimal control, but other types of problems such as minimax control, games, and so on. Then we are going to provide a comparative overview for various special cases of the model. Semi-contractive models, but also contractive models, and also a few other models, including monotone increasing models and monotone decreasing models. We're going to explain what this means as we go along, but the results differ depending on particular structures that you may have in the model. Then we're going to focus on semi-contractive models, which are the principal case of interest to us in this series. And we are going to provide analysis which parallels the one that we gave for stochastic optimal control. So let us introduce abstract dynamic programming. The objective of the subject is to unify the core theory and algorithms of total cost sequential decision problems in a general setting. By general, we mean that we're going to treat simultaneously a variety of problems. Stochastic optimal control is one example. Markovian decision problems, including semi-Markov problems, is another. Minimax problems, sequential games, problems involving multiplicative cost and risk-sensitive criteria are going to be all special cases of a broad framework that we are going to introduce. The idea here is to define a problem by the mapping defining its optimality or Bellman equation. This mapping is the mathematical signature, so to speak, of the problem, in the sense that the properties of this mapping determine what kind of results may be proved for the corresponding model. So depending on whether the structure of the mapping has certain structural properties such as monotonicity, contraction, or semi-contractive type properties, this will determine the analytical and the algorithmic theory of the problem. We saw in the special case of optimal control problems that a lot of the theory revolves around fixed points of the corresponding dynamic programming mappings, and indeed we are going to continue to see that fixed point theory plays an important role in the analysis. The abstract dynamic programming problem involves a single mapping, and this mapping involves two sets, X and U, which we refer to as the state space and the control space, respectively. We introduce a control constraint set for every state X, this use of X, and we consider stationary policies, which are control functions mapping states to control that satisfy the control constraint. Now the problem is defined by a single mapping that maps X, U, and E sub X, the set of all extended real valued functions on X, into R. In other words, given any x, u, and function j, h of x, u, and j is a scalar for every x and u. Now, the one property that we require of the mapping h is monotonicity. In other words, given any two functions, j prime uniformly larger than j, then h applied to j and j prime preserves the direction of the inequality for all x and u. So that's the monotonicity property, and it's very fundamental to everything that we do with abstract dynamic programming. Now, given h, we can also define the mappings T mu for a given stationary policy mu and the mapping T by these expressions here. So Tj is obtained by minimization over mu of T mu. And this is all reminiscent of the notation and the meanings of stochastic optimal control. Indeed, stochastic optimal control is a special case that involves a mapping, the mapping that comes into Bellman's equation, that involves the cost per stage and the system function, where x and u are state and control, w is a random disturbance, and we take the expected value with respect to the random disturbance to get a number here, h, x, u, and j. So this is a special case of a mapping that satisfies the monotonicity property in view of the plus sign here and the fact that alpha is a discount factor greater than 0 and less or equal to 1. And so the notation that we use here is consistent with the notation that we use in stochastic optimal control. Now, given a monotone mapping H and the corresponding mappings T mu and T, let us consider an abstract dynamic programming optimization problem. We're given an initial function j bar, which is a real valued function, and a policy. For any policy mu, we define j mu, the cost function of mu, as the upper limit of the quote-unquote finite horizon costs corresponding to mu. In the context of stochastic optimal control, this is the end-stage cost of using policy mu starting from state x and having as terminal cost j bar. In the case of stochastic optimal control, j bar is equal to 0. Here, in general, it can be any function that's real valued. So for every policy mu, we have the cost function. It's a real number for every x. Take the infimum over all mu, and we obtain the optimal cost function. That's what we want to find. We want to find j stars of x for all x, and an optimal mu that attains the infimum uniformly for all x. Now, the theory that we are going to discuss, consistently with our experience with stochastic optimal control, will revolve around fixed point properties of the mappings T mu and T. In other words, we're going to be interested in whether these equations hold, which are generalized forms of Bellman's equation. And the algorithms for solving this abstract problem are going to be special cases of fixed point algorithms, but under circumstances where there does not necessarily exist a unique fixed point of these mappings, and T mu is a contraction mapping, and so on. And for the moment, we're going to restrict attention to issues involving only stationary policies. So we want to find the infimum overall stationary policies here. In some contexts, there may be interest in exploring the potential of non-stationary policies, and occasionally we'll have an opportunity to comment on this issue. Let us now consider some examples of abstract dynamic programming problems. The first example is the familiar stochastic optimal control problem, where we have a one-stage cost function g and a discrete time dynamic system whose equation evolves according to this function f. W is a random variable, and here we're taking the expected value with respect to W. This is the mapping T mu, and if we take J bar, the terminal function, to be identically 0, then the cost of a policy is defined by taking the end stage costs, add them up, appropriately discounted, taking the expected value of that, and then taking lim sup as n goes to infinity. Let's consider minimax type of problems, which are similar to the stochastic optimal control problems, except that instead of an expectation, we have a supremum, and instead of stochastic uncertainty, we have a W that's being chosen by antagonistic opponent from some set that may depend on X. And again, we have a one-stage cost function and a system function defined by F. This is the mapping T mu, and taking again J bar to be identically 0, the cost of a policy starting from x0 is obtained by taking the finite horizon n step costs and taking the worst case of that, not the expectation, but rather the supremum over all the W, and then taking the limit as n goes to infinity. In multiplicative cost problems, again, we have a one-stage cost function G and a system function F. However, the cost does not accumulate additively, but rather multiplicatively. So here's the function, here's the mapping T mu, and here's the function J bar is taken to be identically equal to 1. And to obtain the cost of a policy starting from initial state x0, we consider the end stage cost, but accumulated not additively, but multiplicatively, taking expected value over the stochastic variables W, and then taking the limit as n goes to infinity. Let us also consider some examples involving a Markov chain, either a chain with a finite number, let's say n number of states, or perhaps a countable number of states. The Markov chain is defined by transition probabilities from a state ik. You go to state ik plus 1 according to this probability, which may depend on the control that we apply. And the mapping T mu here is given in terms of the transition probabilities, the one-stage cost, and there's also a discount factor that depends on the state where you start, the state when you end up, and the control. That's a difference between between these problems. Is a state and control dependent discount factor. This type of problems are also called semi-Markov in the theory of Markov decision processes. Still, we have the expected value of the one-stage cost plus the expected value of the cost to go. And again, J bar is equal to 0. And to obtain the cost of a policy, mu at the initial state I0, we consider the sum of the costs over n periods appropriately discounted. Now, the expression for the cumulative discount factor up to time k is obtained by multiplying the discount factors, which depend on the corresponding states and controls. And taking the expected value of that, which involves these transition probabilities here, and then taking the supreme as n goes to infinity, gives us the cost of a policy. Another class of problems involving Markov chains is a shortest path type of problem, but it does not have an additive cost function, but rather an exponentiated cost function. In particular, here we have a termination state t, and the cost of a policy starting at state 0 is obtained by computing the sum of the costs over n periods, exponentiating that, and then taking the expected value with respect to the transition probabilities. And the use of an exponential here has the effect of giving the cost a risk-averse character. In particular, large values of this sum are penalized much more than small values. So this is the expression for the cost, taking the minimum, taking the limit as n goes to infinity of the finite horizon cost, and this has a multiplicative character because exponential of a sum is equal to sum of the exponentials. If we take j bar equals to 1, like in the multiplicative cost problem of the preceding slide, we end up with a mapping T mu that has this form here. An interesting characteristic of this mapping is that it is linear in the cost function j, linear plus constant, or affine. Problems with this kind of structure, we call them affine monotonic, and we will encounter them later. Let us provide a classification of abstract dynamic programming models. Generally, the mapping T mu and its properties determine the results that we can prove for a given model. Of course, a fundamental property of T mu is that it is monotone. Another important property is when T mu is contractive, when all the mappings T mu are contractions within the set of bounded functions, b sub x, with respect to a common weighted subnorm and a common contraction modulus. A primary example of such models are discounted stochastic optimal control problems with bounded cost per stage. Another class of interesting models is when T mu is such that it increases j bar or it decreases j bar. Accordingly, these models are known as monotone increasing or monotone decreasing. There are some classical dynamic programming models from stochastic optimal control that date to the 60s, which involve non-negative cost per stage. They're called negative dynamic programming models because they involve maximization of negative cost. And the reverse case, where the cost per stage is non-positive, and they come under the name positive dynamic programming models because again they involve maximization rather than minimization. These models have been studied for some time and have some nice properties, including the fact that Bellman's equation always holds for these models. On the other hand, they have some weaknesses. We also have semicontractive models that we have discussed, where some of the mappings T mu have a contraction-like property and others do not. These models are sort of complementary to the monotone increasing, monotone decreasing models. They do not have a guarantee that the Bellman's equation holds for. On the other hand, they have some nice properties under certain assumptions that these monotone increasing and monotone decreasing models do not have. A special case of semicontractive models is when the function j bar is non-negative, and also these models operate in the space of non-negative functions. So starting with a non-negative function, T mu always gives you a non-negative function. One example of such a model we saw in a previous slide, the one that involves exponential cost function, and it's an example of an affine monotonic model. In affine monotonic models, this is an assumption that we make, and we are going to encounter these models later in this series. Let us now provide an overview of the results that we can obtain for the models of the preceding slide. Regarding Bellman's equation, it doesn't always hold under the various assumptions. For some models it holds, for some others does not. For the cases of a contractive model, a monotone increasing model and a monotone decreasing model, Bellman's equations always hold, although for the last two models, the monotone increasing and monotone decreasing, it may not have J mu or J star as its unique solution. For the semi-contractive models, the Bellman equation holds for the regular policies, and the Bellman equation for the overall problem typically will hold for the restricted optimal cost function j hat, under our assumptions at least, but we may have j star different than j hat. Let us now elaborate and summarize the issue of uniqueness of solution of Bellman's equation. For the contractive case, T is a contraction within the set of all bounded functions over X, and J star is its unique fixed point. Bellman's equation has a unique solution. In the monotone increasing and monotone decreasing cases, Bellman's equation has J star or J mu as a solution, but it may have multiple fixed points. In the semicontractive case, J hat, the restricted optimal cost function, is a unique fixed point of T within a subset of regularity of the space of real valued functions. The most powerful results hold only for that case. In the case where we have a semicontractive model that in the space of positive functions, J star is the unique positive fixed point of T, or perhaps non-negative in some cases, consistent with the previous case. Let us also take a look at optimality conditions for a stationary policy. This is a little complicated story. In particular, for the contractive case and the monotone increasing case, and also the semicontractive case under the stronger set of assumptions, like the strong PI property, we have that mu star is optimal even only if it satisfies this condition, it attains the minimum in Bellman's equation. In a semicontractive case under a weaker set of assumptions, the weak PI property, this condition also holds, but mu star has to be regular, so this is a little bit more restrictive condition. In the monotone decreasing case, there's a different condition. Mu star is optimal even only if mu star attains the minimum in Bellman's equation, but with J mu star in the equation. This is different than the one under the contractive and monotone increasing cases, and this is also a little harder to verify. Let us also summarize the results for the value iteration method and its convergence. The value iteration method takes this form. You start from J0, generate Tj0, then T squared J0, and so on. In the contractive case, things are nice as usual, and the value iteration method converges to J star for every starting point, every bounded starting point. Case D is also somewhat favorable because we have convergence to J star, but the starting point is the initial function J bar, or terminal function if you wish to call it that, and also for some other initial conditions, but the main one is this J bar. For initial conditions, for example, that are smaller than J star, you do not have convergence. In the monotone increasing case, you don't always have convergence to J star starting from J bar. There are some additional conditions that are needed, like the compactness conditions that we have seen in the context of semicontractive models. In the semicontractive case, we have convergence to J hat and perhaps to J star for all initial real valued functions, at least under some assumptions, but for all J within the set of regular behavior, within the set of the well-behaved set, the set of all J that are greater than J hat and belong to the set S. And depending on the assumption, you may have somewhat stronger results. In the case where you have semicontractive models within the space of positive functions, you get similar convergence result for all the initial conditions are the positive J or the non-negative J, depending on the conditions. But it's a somewhat complicated story with different special cases. Let us also look at policy iteration. Again, we have a somewhat complicated story. Recall that each iteration here consists of two phases. One is a policy evaluation, where we evaluate J mu K by solving the corresponding Bellman's equation, typically, for the current policy mu K. And then we have the policy improvement phase, where we generate the new policy mu K plus 1 by minimization in the corresponding Bellman equation. This is the classical form of policy iteration, and for the contractive model, it converges to an optimal policy starting from any initial policy. In the semi-contractive case, as we discussed in the preceding lecture, we have convergence starting with a regular initial policy, and we have to take precautions that no irregular policies can arise, which will happen under the strong PI conditions. In the case of monotone increasing, monotone decreasing models, we may have convergence may fail, as we have seen through examples. Under certain conditions, of course, convergence can be guaranteed. Let's look also at an approximate form of policy iteration called optimistic or modified, which combines value iteration and policy iteration. Here, instead of calculating the cost function of the current policy exactly, we calculate it approximately by a number, some finite number of value iterations. And you still, this is a well-established form of policy iteration, and it works faster than the classical form in most cases. Regarding its convergence, for the contractive model, we have convergence starting with any initial condition and any initial policy. In the semi-contractive case, we're going to examine this a little later in the last lecture. We have convergence under some conditions, but only after a substantial modification in the policy evaluation step. Briefly, we create a certain stopping problem, imposing an artificial stopping action which keeps the iterates bounded. So this is quite different, but you have reasonably good convergence results. In the case of the monotone decreasing model, we have convergence starting with the J bar initial condition for the value iteration that approximates J mu 0. In the case of the monotone increasing model, we may have failure, as we have seen with examples, and shortest path deterministic shortest path examples in particular, and special conditions may be required for convergence. Let us also mention an asynchronous form of optimistic policy iteration, which again combines value iteration and policy iteration, but these iterations are done asynchronously. For some states, we may be doing value iteration. For other states, we may be doing policy iterations, and there is the data that we use in these iterations may contain communication delays, which is a hallmark of asynchronous operation. We're not going to talk much about this, but just to record the results here. In the contractive case, the standard form fails because of asynchronism, and some modification is required, the type of modification we discussed here in terms of a stopping problem. Again, the same is true for the semi-contractive model, and for the monotone decreasing and monotone increasing models, convergence may fail altogether, and some special conditions are needed, and the subject is not the situation is not entirely clear here. Some further research is necessary. Let us also mention approximate dynamic programming, a methodology that's at the forefront of current research. A principal application of approximate dynamic programming is in problems where the state space is very large, either finite but with a very large number of states, or infinite. A major approach here involves approximation of J mu and J star within a subspace that's spanned by basis functions. This may result in significant dimensionality reduction and makes algorithms such as value and policy iteration applicable. The approach here was to use approximate versions of value and policy iteration, and in so doing, very large and complicated problems have been addressed with considerable success. Simulation is also very important in these algorithms, and this has an additional advantage that no mathematical model is necessary to execute these algorithms. Just a computer simulator of the control system is sufficient. Regarding the application of abstract dynamic programming, a key property is monotonicity. So when you construct an approximate model, you need to preserve the monotonicity property in order for abstract dynamic programming to apply. And this is true for one of the major methods of approximation called aggregation. This has the required monotonicity property, but for other models, this property is not available. So the theory that we have for abstract dynamic programming at the moment does not apply. For specific types of models, the most well-behaved case is the contractive case, for which there is a wide variety of results which hold thanks to the underlying contraction property. There is a version of value iteration that's approximate. There is also the Q-learning algorithm, which is an important algorithm within this context, and approximate forms of policy iteration, both pure and modified. In the case of other models, there are hardly any results available in the context of approximations. On the other hand, the case of a stochastic shortest path problem, which is important in applications, a special case of semicontractive model, has been discussed in some detail, and the analysis there under favorable assumptions is almost as powerful as the one for the contractive case. Okay, let us now go into semicontractive models, our main subject in this lecture series, in some more detail. Let's review the definition of the semicontractive abstract dynamic programming problem. The starting point is a mapping H, which maps states, controls, and functions of state into real numbers, and it has the fundamental monotonicity property. If J prime is uniformly larger than J, then applying X to them preserves the sign of the inequality. Given H, we have also the mappings T mu for each policy mu, and T given by this expression here. T is the minimum overall policy of T mu, and T mu of J is a function. So T mu maps functions into functions, and the same is true for T. We are given an initial function J bar, and for every policy mu, we define the cost of the policy starting from state X as the lim sup of the end stage costs of mu starting from X, and we want to find the optimal value of J mu over all mu, and a policy mu that attains the infimum. Now, the key idea in semicontractive models is a set of functions S, which is viewed as the domain of regularity, and policies are divided into regular with respect to this set of functions, or irregular. And the precise definition is as follows. Given a set S, we say that the stationary policy mu is S regular if J mu is a fixed point of T mu within S. Moreover, if you apply value iteration starting from any J within S, you obtain in the limit J mu. No matter where you start, value iteration converges to J mu. So J mu can be viewed as a unique stable equilibrium of T mu within S. And we say that a policy that's not S regular is called S irregular. And we will now proceed to discuss the basic properties around S regularity. A key idea in semi-contractive dynamic programming is to consider a restricted optimization problem whereby we optimize over the set of S regular policies. So we consider this problem, minimize J sub mu over mu in the set M sub S of all S regular policies, and we call Js star the optimal cost function of that restricted problem. So viewing functions J over the real line here, the cost functions J mu over the S regular policies lie in this line, and the minimum over those is Js star. All of these, of course, lie within the set S by definition of S regularity. However, the optimal cost function over all policies need not be equal to J stars of S. Since J stars of S is a subset of the set of all policies, J star is optimization over a larger set, and it may be, it is no greater than Js star and could be strictly less than Js star. We will now discuss the main results of semi-contractive analysis in an abstract setting. It turns out that all the results we derived for the special case of stochastic optimal control in the second lecture can be extended to the general abstract semi-contractive problem and with essentially the same proof arguments. So in what follows, we will just go over the basic results without proofs. In particular, we have this well-behaved region theorem, which says that if Js star is the restricted optimal cost function, then there is a certain region demarcated by Js star on the left and by the maximum function in S on the right. And if Js star is a fixed point of T, then the model behaves well within this region. So the first result is that Js star is the only fixed point of T within the set Ws. The second result is that if you start value iteration from any function within this well-behaved region, then you converge to the restricted optimal cost function. The third result is an optimality condition. If mu star is S regular, Js star belongs to S, and mu star attains the minimum in this Bellman equation, then mu star is optimal within the restricted class of S regular policies. Conversely, if mu star is restricted optimal, then it attains the minimum in Bellman's equation. The issue now is how do we show that Js star is a fixed point of T? In this lecture series, we are going to focus on a policy iteration-based approach. This approach applies when S is well behaved with respect to policy iteration, which roughly means that policy iteration generates S regular policies if it started from an S regular policy. The significance of having the generated policies be S regular is that then you can show that the sequence of policy cost functions is monotonically non-increasing. In other words, there's a cost improvement property going on when you're dealing with S regular policies in the context of policy iteration. The proof of this is very simple. Mu k is a S regular policy, is the current policy. It satisfies this equation by S regularity. We have this inequality holding and by the definition of the policy improvement operation, mu k plus 1 is generated as the policy that satisfies this equation. So we have that that T mu k takes J mu k downwards, and by S regularity again, and using the monotonicity of T mu k plus 1, we have that the next policy is going to be an improved policy over the current policy. So this sequence is monotonically non-increasing, and therefore it has a limit, J infinity. Now, what would the limit be? This policy's cost functions converge downwards towards Js star. Js star is the minimum over all the J mu's for mu S regular. So you would expect that if the limit can be taken through this relationship, first of all, J infinity will be a fixed point of T, and also that the limit is going to be equal to Js star. So in this way, we can prove that Js star is a fixed point of T under conditions that allow us to take the limit in this relationship. Now, we are going to introduce two different kinds of policy iteration properties, which we saw in the context of stochastic optimal control, a weak property and a strong property, and obtain corresponding weaker and stronger results for Js star to be a fixed point of T. Let us now give two basic theorems of semicontractive analysis relating to PI properties. We say that S has the weak policy iteration property if it is possible to generate a sequence of S regular policies by policy iteration. In other words, if there exists an initial policy mu0, that's S regular, and starting from that policy, the policy iteration algorithm can generate a sequence mu k consisting of S regular policies exclusively. Now notice that this property does not say that every sequence that starts with an S regular policy is going to consist of S regular policies. It only says that there exists one. And the result says that if you have the weak PI property, and if you have in addition a continuity from above property of H, in the sense that for every sequence of functions that are monotonically non-increasing to J, for some J, we have that the corresponding sequence of H values converges to the value of J. So this is like continuity from above, and it's automatically satisfied in stochastic optimal control problems. For general abstract DP problems, we have to assume it. Now, assuming these two conditions, the result says that Js star is a fixed point of T, policy iteration converges to Js star, and Js star is the only fixed point of T within the well-behaved region, and moreover, starting from within that region, value iteration converges to Js star. Let us say that S has the strong PI property if policy iteration, when started from an S regular policy, will generate exclusively S regular policies. And also if the weak PI property holds, so that there exists at least one sequence of regular policies that can be generated by PI. So observe the difference between the strong PI property and the weak PI property. In the strong PI property, we assume that all sequences that can be generated by PI, starting from a regular policy, are all regular. In the weak PI property, we assume that there exists some sequence of regular policies that can be generated by PI. Now, how do we verify the strong PI property? We will restrict ourselves to the case where S consists of real valued functions exclusively, and it can be shown that the strong PI property holds if there exists at least one S regular policy, if this set is compact for all J in S, states X and scalars lambda, It's a subset of the control space, which is assumed to be a metric space, and we assume that this is compact for all j, x, and lambda. We introduce a similar compactness condition for the case of stochastic optimal control. This is essential in order for policy iteration to be able to be carried out, for the infimum in Bellman's equation to be attained, and so on. Finally, the third and most important condition is that for every S irregular policy, there is a state such that mu starting from that state has infinite cost. Not only that, this happens not only when j is equal to j bar, but also for every j in S, which means that the limit of the finite horizon cost with terminal cost function being equal to j for some state x is infinite. Among others, this guarantees that S irregular policies cannot be optimal, because if j is replaced by j bar here, then the cost function of the policy is infinite starting from some initial state. On the other hand, we know that there exists at least one S regular policy which has a real valued cost function. So an S irregular policy cannot be optimal. If there is a policy that's optimal, it must be S regular. So that's the condition that is important here, which can be arises naturally in the context of applications. Let us now discuss an implication of the strong PI property. If we assume that the conditions of the preceding slide, which guarantee that the strong PI property holds, are in effect, and we also assume that Js star, the restricted optimal cost function, belongs to S, then Js star is the unique fixed point of T within S. Value iteration converges to Js star from every J in the well-behaved region, Ws, and we have an optimality condition. Every policy mu that attains the minimum in Bellman's equation with Js star being used is optimal within the restricted for the restricted problem, and there exists at least one such policy. Now, this condition is similar but a little stronger than the one that we obtained under the weak PI property. In particular, Js star is the unique fixed point of T within S, not just within the smaller set Ws. Moreover, we have this optimality condition, which also provides for verification of existence of an S regular policy that's optimal for the restricted problem. It turns out that under a stronger assumption that still revolves around the strong PI property, we can prove some very strong conclusions. Let us first state the assumption in some detail, and then we will discuss the conclusions. The first part of the assumption states that the conditions for verifying the strong PI property that we gave hold. In particular, S consists of real valued functions. There exists at least one S regular policy. This set is compact for every J in S, X, and lambda scalar. Also, for every S irregular policy, there is some state from which the policy has infinite cost. And this is also true when the terminal cost function is not just J bar, but it can be any J in S. Moreover, additional assumptions are that S contains J bar. So J bar is real valued. Moreover, S has the property that if you have two functions J1 and J2 in S, then S contains all functions of J in between J1 and J2. This is a technical assumption that typically holds in applications. In particular, it is true if S is equal to R sub X or is equal to the subset of non-negative functions in R sub X. The second additional condition, is that Js star belongs to S. The restricted optimum belongs to S. The third condition is a technical one. It's a continuity from below condition for every sequence Jm in S that converges from below to monotonically to some J in S. we have that the corresponding sequence of values of h converge to the value at the limit for all x and u. Finally, there's another technical condition that says that given S, you can bound it from below by J prime in S such that J prime, when operated on by T, goes upwards. This is a technical condition. We encountered it in somewhat milder form in the case of stochastic optimal control, and it turns out that to be a tricky condition to be verified on each particular application. We will see how one can verify this condition in specific applications in the next lecture. Now let us state a stronger theorem for the case where S consists of real valued functions. Under the assumptions of the preceding slide, the assumption with the many different conditions, we have the following. J star is the unique fixed point of T within the set S. Value iteration converges to J star starting from any J in S. We have a necessary and sufficient condition for optimality. Nu is optimal if and only if it attains the minimum in Bellman's equation. Moreover, there exists at least one optimal S-regular policy. This is a consequence of the compactness condition, which guarantees that the minimum in Bellman's equation is attained. We have another condition that's helpful in algorithms, as we are going to see in the next lecture. For any J in S that is such that T, when applied to J, increases the value, we have J being less or equal to J star. And reversely, if T takes J downwards, then J is greater than J star. So another way to state this condition is that J star is the maximum J in S that satisfies this inequality. We will see that this will give rise to a mathematical programming algorithm, an optimization problem for finding J star as the maximum of all J in S that subject to certain inequality constraints expressing this inequality. And there's a symmetric problem. J star is the smallest J in S that satisfies this inequality. Finally, regarding policy iteration, if we have a certain technical continuity condition holding whereby for any Jm that converges to J for some J, we have this condition, this continuity condition holding, then every sequence mu k generated by the policy iteration algorithm starting from an S-regular policy converges monotonically to J star. Note that the conclusions of this theorem are almost as strong as the ones for contractive problems. While there are some assumptions to verify in particular applications, most of these assumptions follow naturally from the structure of the problem, and we will see examples of how the various assumptions can be satisfied in two examples beyond stochastic optimal control in the next lecture, which will involve shortest path type of problems, both of the min-max type and also of the exponential cost character.